Well, let's talk about the fundamental theorem of calculus. And a lot of times it's referred to as the first fundamental theorem of calculus. There are two fundamental theorems of calculus that kind of related to integrals, and this one comes first, so we tend to call it the first, or sometimes we just leave that the prefix off of first. We just call it the fundamental theorem of calculus. So this example is starting, and it's giving us a function. Capital F of t is representing the position of a particle on the x-axis as a function of time. So we have a graph down here which just models the general curve, and what we can see is that this particle obviously starts at 16 on the x-axis, and it's decreasing until 4 seconds when it hits the x-axis at 0. So for this, let's just assume we're going to look at that interval of time from 0 to 4. So what we have here, just to be clear, this is a position function. So if we have the position function, there's some questions that I'm going to start to introduce that are very easy to do. So for example, I could ask us, what is the change in position from t equals 0 to t equals 4? Well, this problem's simplified because if we're looking for a change in something, right, we see that word change. That's just a difference. So we are going to subtract two things. So where did you end compared to where did you start? That is the definition of the change in position. So in this case, where we ended was right here, that's 0, and where we started was up here at 16. If we use function notation, the position is given to us by this function. This is f of 4, excuse me. And I subtracted the position at 0. So since we are given position, we can directly calculate the change in position using the position function. Just another question, if I wanted the change in position from, let's just say, 2 seconds to 3 seconds. Well, at 2 seconds, it's right here, and at 3 seconds, it's right there. So at 3 seconds, the function's value is big F of 3, so that's where I ended up, which is going to be 7. And then at F of 2, which is where I started on this interval, that position was 12. So I decreased on the x-axis by 5 numbers. So again, it's very easy to do questions about change in position, especially if we are given the position function. So transitioning, I just have a graph that's slightly different here. So I did copy the original position function, f of t. So we know that the blue is representing the position. All right, big F of t is position. Now what I've graphed in red below it is actually the derivative of the position function. So this is f prime, so capital F prime of x. So this was the derivative of f, sorry, that's t, not x, my bad, f of t. So what we were looking at on the last slide was change in position. So if I wanted to measure the change in position, we went through one method on the last slide. We're going to go over another method here. Let's pretend I started here. So we started at t equals 0, which is right here. If I wanted to figure out my change in position, so in other words, how did my distance change over time, what I would have to do is I'd have to take a time frame and multiply it by my velocity. And that would tell me where I went. So for instance, if I started here, and for this case, let's just look at 1 second intervals of time. So on this 1 second, the duration of time was 1 second. And then I would just multiply that by whatever my velocity was. And my velocity, in this case, let's just measure it in units, is going to be units per second. So I can estimate the change in my position. I mean, I can obviously see, just using the values, what that change in position was, but I could estimate it. So for instance, if I had 1 second and I was traveling 3 units a second, my change in position would be 3. What we can do is we can actually use the velocity function to measure how far we made it in that interval. So if we look at the first interval, which I just have as the first second of time, what we can see is over that 1 second interval, right here on the x-axis, the velocity is changing. It's not always constant. It's not like I'm moving at 10 units per second or 5 units per second. It's a changing amount. So what I can do to estimate it, I am going to say, well, I traveled for 1 second for sure. Now over this interval here, my speed is changing. So let's just assume that the average speed, so the speed here is 0, and then down here, this is the number -2. Let's just take an average. Let's just say over that interval, I was traveling at -1 units per second. So what I would get here is that change is just -1, which would make sense. I started at 15, and then my y value here after 1 second, I started at 16. And then after 1 second, I was at 15. So I could keep doing that over and over and over again, right? So here I could take another 1 second, and I could multiply it by whatever the speed I was traveling on that interval. So again, what we see is that speed wasn't constant. So for 1 second, how fast was I going? Well, I started going at a velocity of -2, and at the end of that, I was at a velocity of -4. So I could just average it out and say over that second, my velocity was 3. So I got a distance of -3 less than where I was, which makes sense to me, right? Because right here, after the next second, I'm at the point 2, 12. So all we're doing here is we're taking a time for each interval and multiplying it by some sort of velocity. Now maybe we're estimating that velocity, or maybe we actually know it exactly. So here, again, we'd take a small change in time, which is that 1 second, and say over that 1 second, how fast were we going? And we'd be able to figure out an estimate in our change in position. But if we look at this, what we're doing for each change in position of the position functions, we're taking a time. So in other words, we're taking a change in time and multiplying it by the velocity. But that's what we do when we're looking for the integral of a velocity function, right? If I think about calculating the area between our velocity curve down here, which is capital F prime of t, and the area between that and the x-axis, what I do here, this area is just a triangle, right? So the triangle has an area, a width of 1, so this is 1 second of the width, and I'd multiply it by the height, which is -2, so I'm just going to make myself a little more room here. So the width was 1, and that comes with a label of seconds. The height, so the value of the function there, was -2, and that comes with a label of units per second. So this triangle, after I multiply it by half, has an area of -1. Now this triangle here, or this shape here I should say, we'll split into 2 different areas to calculate. So this rectangle has a base of 1 second, and it has a height of -2 seconds. So the area of the rectangle is -2. I'm going to erase some of my work here, so I have a little more space to show the next. So for this triangle, which is on the bottom there, we can calculate that area. So this area here, the triangle has a base, again, of 1 second. Now the height of this triangle, well, this is the velocity of -2. This is the velocity of -4. So the height is -2. And then we take 1/2. So this triangle also has an area of -1. So this entire thing has an area of -3. Now what we're going to notice is we can keep calculating that area, but all we're doing is we're trying to get you to notice that I could use the original position function and say if I started at 16 and ended at 15, I can easily see the change in position was 1 unit, which happens to match up with the area of this shape. We look at the next section that we did. We said, well, if I have a position function and I started at 15 at second 1 and I ended up at position 12 after second 2, I can easily see my change in position went down 3, which happens to match directly with the area of the shape down here. So we'll continue to do that if we were to do all the examples, but this change in position is going to match this area here. And this change in position will match this area here. So let's try to summarize our argument. On the first page, what we were able to do is we looked at the difference in position of our position function on the interval 0 to 4. So if we looked at the change in position, we can easily see that this particle, or whatever is moving, it started right here. So at time 0, it was at 16. And then it ended here. So at time 4, it was at position 0. So the change in position is measured by this, right? Where it ended up, which was 4, compared to where it started, was an input of 0. So f of 4 was 0, f of 0 was 16, so our change in position was negative 16, which makes sense. It started on the x-axis at 16, and it ended on the x-axis at 0, so it was negative. What we then connected it to was if we looked at this other function. So let's say we have the derivative of that function. What we can do is if we looked at the area between the curve of the derivative, which is a straight line here, and the x-axis, what we see is this shape here, which I'm outlining in red, this shape is clearly a triangle. Now we can calculate the area of this triangle, and we're going to include units, and we'll go back and compare it to the units that we started with. So this triangle has a base of 4. Now that number 4 is on the t-axis, so it inherently comes with a unit of seconds, just a unit of time. We're going to assume it's seconds. Now for the height of that triangle, right here, 0, on this point here is the derivative at, and it looks like it's negative 8, right? So the height here is negative 8. Now since this was a change in position, it was a change in the units of distance compared to time, which we're just assuming as seconds. And since it's a triangle, we have 1/2. So we can see here is when we calculate this area is negative 16. And there's no coincidence that the area of this is the same as the change in position. So let's summarize. So the first thing we're going to do is change the notation just slightly so we can avoid some confusion. So here we have big F of t, and right down here we wrote it as big F prime of t, just so we could better indicate the relationship that the red thing was the derivative of the blue thing. So what we say then is we're going to let the function lowercase f of t be the derivative of uppercase f of t. So we can think of this just as the lowercase f of t. Now what we saw was that if we took an integral, and in our case we went from 0 to 4, if we took an integral of our derivative, what that meant was we were just adding up a bunch of areas. So the height of our area was measured by the function, and the width of our shape was whatever change in time we set it to. And what we noticed was that function, which gave us 16, was the same exact thing we got if we evaluated the original function like this. So in other words, specifically, if we integrated from 0 to 4, what we did before was we took f of 4 and we minused f of 0. And we saw that these things were always the same. It always gave us negative 16. So in general, this brings us to the fundamental theorem of calculus. if we have a function that is the derivative of a bigger function, the integral of the derivative will always equal the change in the original function.